There is a hidden language that holds the modern world together. It isn't written in code or spoken in tongues. It is carved into steel at a 60-degree angle. Without the boring uniformity of the common screw thread, every plane would fall from the sky, every bridge would buckle, and the chair you're sitting in would cease to exist. Tonight, we journey into the meticulously dull, surprisingly high-stakes world at how humanity finally agreed on how to twist metal. Imagine a world where nothing fits. It's 1830. A steam locomotive breaks down in a remote village. The engineer reaches for a spare bolt, but it's useless. His bolts were made in London. The engine was built in Manchester. In this era, every screw was a unique work of art, which made the industrial world a logistical nightmare. This is the story of how we traded that artistic chaos for the beautiful, sleepy comfort of the standard. Before we dive into the dusty archives of the 1841 Whitworth proposal, I want you to settle in. Imagine the sound of a heavy iron lathe in a workshop in 19th century England. The steady, rhythmic shaving of metal. The smell of oil and cold steel. We are going to slow down time, one thread at a time. Picture this. You're building that new bookshelf and a screw is missing. No problem, right? You just run to the hardware store and grab a new one. But imagine a world where that simple trip wouldn't solve your problem. A world where every single screw is one of a kind. Welcome to the early 19th century, the era of what we'll call mongrel threads 1. Before 1841, standardization as we know it was basically science fiction. If you were a blacksmith or a mechanic, you didn't just make a machine. You made every single bolt, nut, and screw that went into it. Each workshop was its own little kingdom, with its own unique system for creating fasteners. Your screws were your signature, and they wouldn't fit anything made by the guy in the next town over, or even the guy across the street. Each workshop was its own little kingdom with its own unique system for creating fasteners. Your screws were your signature, and they wouldn't fit anything made by the guy in the next town over, or even the guy across the street. Think about the sheer chaos this created. Let's say you're the proud owner of a brand new steam-powered loom. It's a marvel of engineering, weaving cloth faster than ever before. But one day, with a loud snap, a critical bolt breaks. The machine grinds to a halt. Your entire operation is down. What do? You can't just order a new replacement part. There's no catalog, no part number. Your only option is to call the original machinist who built the loom. If he's still in business, and if he's not too busy, he might be able to make you a new one. But more likely, you'd have to take the broken bolt to a local smith. There's no catalog, no part number. This craftsman would then have to painstakingly measure the hole, guess the thread pattern, and hand file a brand new bolt from a solid piece of metal. This wasn't a quick job. It could take hours, even days, of meticulous labor, all while your expensive machine sits idle, losing you money every second. This was the quiet, inefficient world of custom everything. Interchangeability was just a dream. Every repair was a custom job. Every machine was an island, filled with unique components that had no twins anywhere else in the world. Now, expand that problem to a national scale. The Industrial Revolution was in full swing. Railroads were stretching across the country, connecting cities and transforming economies. A locomotive was an incredibly complex machine, made of thousands of individual parts, including countless bolts and screws. Imagine a locomotive chugging along, hundreds of miles from its home workshop. A bolt rattles loose and falls off. Or worse, it shears under the immense pressure. The engine is crippled. The crew is stranded in the middle of nowhere. What's the plan? They can't just radio for a spare part to be sent. Even if they could, the spare part from another locomotive wouldn't fit. The maintenance yard for that railroad would be a logistical nightmare. Instead of bins of standardized bolts, they'd have a massive, disorganized collection of custom-made fasteners from every locomotive they owned. When a repair was needed, a mechanic would have to sift through this mountain metal, hoping to find a close match. And if they couldn't find one, you guessed it, they'd have to fire up the forge and make a new one from scratch. This created enormous delays and incredible expenses. A simple repair could sideline a multi-ton engine for days. For an industry that depended on speed and efficiency, this was if they couldn't find one, you guessed it, they'd have to fire up the forge and make a new one from scratch. The dream of a truly connected industrial nation was being held back by something as small and seemingly insignificant as a screw thread. This problem wasn't just limited to big machines like trains and looms. It affected everything, from scientific instruments to household clocks, from firearms to farm equipment. If something broke, fixing massive ordeal. There was no shared language of mechanics, no universal standard that allowed parts from one place to work in another. The world was filled with these mongrel threads, a chaotic mix of shapes, sizes, and pitches. Each one was an invention of necessity, born in a specific workshop for a specific purpose. While this system showcased the skill of individual craftsmen, it was horribly inefficient on a larger scale. It stifled innovation, complicated repairs, and made mass production almost impossible. The entire industrial world was crying out for a solution. It needed a system. It needed a standard. Someone had to step a specific purpose. Someone had to step in and bring order to this mechanical chaos. The stage was set for a quiet revolution, one that would be led not by a general or a politician, but by an engineer with a vision for a simpler, more connected world. The man who would step up to this challenge was Joseph Whitworth, and his idea would change manufacturing forever. But before we get to his brilliant solution, it's crucial to understand just how deep this problem ran. It wasn't just an inconvenience. It was a fundamental barrier to progress. The story of the screw thread is the story of how we learned to speak the same mechanical language, and it all started with untangling this manufacturing mess forever. We saw how this simple machine was waiting for its moment, waiting for one crucial breakthrough to unlock its true potential and revolutionize our world. Today, that moment arrives. Our story picks up at the dawn of a new century, the year 1800, in the bustling, soot-stained workshops of industrial London. This is where we meet a man whose obsession with precision would change everything. His name was Henry Maudslay. Now, Maudslay wasn't your typical aristocratic inventor. He was a hands-on craftsman, a man who understood metal not just with his mind, but with his fingertips. He started his career at the Royal Arsenal, where he saw firsthand the chaos of non-standardized parts. Imagine trying to repair a cannon or a musket in the heat of battle, only to find that the replacement screw doesn't fit. It was inefficient, it was frustrating, and for Maudslay, it was an engineering problem that simply had to be solved. He knew that the key to mass production, the key to a modern industrial world, lay in one thing: interchangeability. And the key to interchangeability? The perfect, repeatable, identical screw thread. But how do you create identical threads? You can't do it by hand. The human hand, no matter how skilled, will always introduce tiny imperfections. One craftsman's fine thread is another's coarse. What Maudslay envisioned was a machine that could cut threads with unwavering mathematical precision. The existing lathes were a start, but they were clumsy. The cutting tool was often held by hand, guided by sight and feel alone. It was more art than science. Maudslay's genius was to take this existing technology and perfect it, transforming it into a machine of unparalleled accuracy. His creation, the screw-cutting lathe, is one of the unsung heroes of the modern age. Let's break down what made his lathe so special. The heart of the machine was something called the lid screw. This was a master screw, crafted with the utmost care, that ran the length of the lathe bed. Connected to this lead screw was the slide rest, another of Maudslay's brilliant innovations. The slide rest held the cutting tool in a rigid, unyielding grip. As the main spindle of the lathe turned the piece of metal you wanted to thread, a set of gears would turn the lead screw at a precise, related speed. This rotation of the lead screw would then drive the slide rest and the cutting tool steadily and smoothly along the workpiece. Picture it. The rhythmic hum of the machine, the steady rotation of the brass or iron rod, and the slide rest, moving with a slow, meditative, almost hypnotic grace. It wasn't a human hand guiding the cutter. It was the cold, hard logic of gears and the perfect geometry of the lead screw. With each pass, the tool would bite into the metal, carving a helical groove. Another pass, a little deeper, and another. The result was a thread not born from estimation, but from calculation. A thread that was a perfect physical manifestation of a mathematical ratio. For the first time in history, you could produce a screw in London and know with absolute certainty that it would fit a nut made on the very same type of lathe in Manchester, or Birmingham, or even one day across the ocean. This was the birth of consistency. Before Maudslay, every screw was an individual, a one-of-a-kind piece. After Maudslay, the screw became a commodity, a standard component. The implications were staggering. Think about it. Suddenly, you could build complex machines with replaceable parts. A steam engine, a printing press, a textile loom. If a part broke, you didn't have to custom fabricate a new one. You could simply order a replacement. This dramatically lowered the cost of manufacturing and repair, and it accelerated the pace of innovation like nothing before. Inventors and engineers were now free to design more complex and ambitious machines, knowing that the components to build them could be reliably produced. Maudslay's workshop became a legendary training ground for the next generation of engineers. Men like Joseph Clement and the great Joseph Whitworth passed through its doors, learning the gospel of precision from the master himself. They took Maudslay's principles and built upon them, further refining the machines and, crucially, beginning the push for a national and eventually international standard for screw threads. Maudslay didn't just invent a machine. He created a new way of thinking. He instilled a culture of precision that became the bedrock of the Industrial Revolution. His lathe wasn't just cutting metal, it was carving the shape of the future. It was a quiet revolution happening not on a battlefield, but in the noisy clatter of a workshop, one perfect thread at a time. This new capability, this power to create perfect, interchangeable threads on demand, set the stage for the next great chapter in our story. With the how now solved, the question became what? What size should the threads be? What angle? What pitch? The world had a tool for creating order, but it was still a mess of competing proprietary thread designs. The battle for standardization was just beginning, and it would be a hard-fought one. Alright, so we've established that the world before standardized screws was a chaotic mess. Every workshop, every craftsman, was basically making it up as they went along. Bolts from one place wouldn't fit nuts from another, and repairs were a total nightmare. The Industrial Revolution was revving its engines, but it was being held back by this tiny yet massive problem. The world was crying out for a hero, a champion of standardization, and it found one in a man named Joseph Whitworth. Now, picture this. It's the 1830s. Steam trains are starting to crisscross the English countryside. Factories are belching smoke, and the world is changing faster than ever before. In the middle of all this, Joseph Whitworth, a brilliant toolmaker and engineer, decides to take on the screw problem. But how do you even begin to standardize something that has infinite variations? You can't just declare, my screw is the best screw. You need data. You need evidence. So Whitworth embarked on what must have been one of the most mind-numbingly tedious, yet incredibly important, quests in engineering history. He began a grand tour of England, visiting every major workshop he could find. He wasn't there to admire the machinery or chat with the foreman. He was there on a mission. He was there to collect screws. Just imagine him walking into a bustling factory, a place of intense heat and noise, and saying, "Good day, sir. I'm here to take a sample of your screws." He probably got some very strange looks. He traveled from Manchester to London, from Birmingham to Glasgow, methodically gathering a massive collection of screws and bolts of all shapes and sizes. It was like he was a botanist collecting plant specimens, but instead of flowers, he had rusty, oily bits of metal. He brought this vast, motley assortment back to his own workshop in Manchester. And that's when the real work began. Whitworth and his team laid out thousands upon thousands of these screws. Their task was to measure every single one. Not just the length or the diameter, but the crucial defining feature, the thread. They had to count the number of threads per inch for each diameter. They had to measure the angle of the V-shape cut into the screw. It was a monumental task of data collection long before the age of computers or digital calipers. This was painstaking work, done by hand, with precision instruments that Whitworth himself had often designed. As they measured and recorded, a picture started to emerge from the chaos. While there was a lot of variation, certain patterns began to appear. For a given diameter of bolt, there seemed to be a rough consensus on how many threads per inch it should have. It wasn't exact, but it was a starting point. Whitworth's genius was not in inventing a completely new thread out of thin air. It was in seeing the wisdom of the crowd, the average preference that had naturally developed over years of trial and error in workshops across the country. He took all this data and calculated the average. For each size of screw, he determined the average pitch, which is the distance between threads. He compiled this into a neat, orderly table. A 1/4-inch bolt should have 20 threads per inch. A 1/2-inch bolt should have 12. A 1-inch bolt should have 8. Simple, logical, and based on what the majority of skilled craftsmen were already doing. This approach was brilliant because it wasn't a radical change. It was a refinement. It was easier to get people to adopt a standard that felt familiar. But what about the shape of the thread itself? The angle of that V-groove? This was another area of total chaos. Some threads were sharp and pointy. Others were more rounded. Sharp threads were weak and easily damaged. Square threads were stronger, but much harder to make. Whitworth needed a compromise, a shape that was both strong and relatively easy to manufacture with the tools of the day. Again, he turned to his mountain of data. He measured the angles on all his sample screws. The angles were all over the place. 45 degrees, 60 degrees, anything you can imagine. After measuring and analyzing countless threads, he calculated the average, and the number he landed on was 55 degrees. It wasn't a nice round number like 60, but it was what the data told him. The 55-degree angle was the sweet spot. To further improve the design, he made one more crucial tweak. Instead of having the V-groove come to a sharp point at the top and bottom, he rounded it off. This was a masterstroke. A sharp point is a natural weak spot, a place where a fracture is likely to start. By rounding the crest and root of the thread, he made the entire screw significantly stronger and more resistant to stripping and damage. It also made them easier to make, as cutting a perfect sharp V is much harder than cutting a slightly rounded one. So, in 1841, after years of collecting, measuring, and calculating, Joseph Whitworth was ready. He stood before the Institution of Civil Engineers in London and presented his findings. He didn't just propose a new standard. He presented the overwhelming evidence he had gathered. He showed them his tables of diameters and pitches. He explained the logic behind the 55-degree angle and the rounded crests. He had done the homework. He had created a system that was logical, practical, and based on the collective experience of the entire British manufacturing industry. The system was called the British Standard Whitworth, or BSW for short. It was the world's first national screw thread standard. The adoption wasn't instantaneous, of course. Old habits die hard. that the advantages were so obvious that it quickly gained traction. The British railway companies, massive consumers of nuts and bolts, were among the first to adopt it. The Royal Navy followed suit. If you wanted to get a lucrative government contract, you had to use Whitworth threads. Soon, it became the undisputed standard across Great Britain and its vast empire. For the first time in history, a mechanic in London could be certain that a half-inch nut would fit a half-inch bolt, regardless of where either part was made. It was a revolution. It streamlined manufacturing, simplified repairs, and dramatically increased the reliability of machines. Joseph Whitworth hadn't just invented a screw thread. He had introduced a new way of thinking, an idea that components could and should be interchangeable. And this idea would go on to change the world in ways even he couldn't have imagined. But while Britain was busy standardizing, a new industrial power was rising across the Atlantic, and they had their own ideas about how to make a screw. And that's where our story will go next. You know, for something we see every day, screws have a surprisingly dramatic and opinionated history. We talked about the birth of standardized threads. Now, we're diving into the great international screw thread debate, the Battle of the Angles. It's the British versus the Americans, 55 degrees versus 60 degrees. This might sound like a tiny detail, but this 5-degree difference tells a story of national pride, industrial philosophy, and a quest for perfection. So grab your calipers and let's get into the nitty-gritty of screw thread geometry. On one side of the Atlantic, we have the British and their champion, Joseph Whitworth. As we discussed, his system, established in 1841, was the world's first national standard. The defining feature of a Whitworth thread is its 55-degree flank angle, with rounded roots and crests. Think of the thread profile as a series of rolling hills. Whitworth's reasoning for this was brilliant. The rounded design was meant to reduce stress concentrations at the bottom of the thread, making the bolt stronger and less likely to crack under pressure. It also created a tighter seal, which was fantastic for applications involving steam or fluids, a huge deal in the age of steam engines. The rounded tops and bottoms were also less prone to damage during handling and assembly. It was a robust, well-thought-out design that quickly became the standard not just in Britain, but across much of the world. For decades, if you were building a bridge, a ship, or a locomotive, you were likely using Whitworth threads. It was the undisputed king. But as with all great empires, a challenger was rising in the West. Across the pond, American industry was booming. They were initially using a chaotic mix of threads, including Whitworth, but a desire for a uniquely American system was growing. Enter William Sellers. In 1864, he presented his own thread standard to the Franklin Institute in Philadelphia. His design was different in a few key ways. Most famously, it featured a 60-degree flank angle. Instead of rounded tops and bottoms like Whitworth's, the Sellers thread had flat crests and roots. The profile looked more like a series of trapezoids than rolling hills. Now, why the change? Was 60 degrees inherently better than 55? Not necessarily. The real genius of Sellers' design was its manufacturability. This is where we get into what some might call boring history, but I think it's fascinating. It's all about the machinist on the factory floor. To cut a Whitworth thread with its precise, rounded profile, you needed special tooling. Creating those rounded cutting tools was a skilled art form in itself. It was time-consuming and required a high level of craftsmanship. William Sellers looked at this and thought, there has to be a simpler way. His 60-degree angle with flat tops and bottoms was a game-changer for production. Why? Because you could create the cutting tool with simple, straight-sided geometry. Any competent machinist could grind a tool bit to a perfect 60-degree point. It was easier, faster, and cheaper to produce. This wasn't just about a different shape. It was a different philosophy. Whitworth prioritized the theoretical strength and ceiling of the final product. Sellers prioritized the ease and economy of making that product in the first place. This focus on mass production was quintessentially American. It was a system designed for a rapidly industrializing nation that needed to make things quickly and efficiently. So the stage was set for a showdown. The British system, with its 55-degree rounded threads, was the established global standard, celebrated for its strength and reliability. The American system, with its 60-degree flat-top threads, was the up-and-coming challenger, designed for speed and ease of manufacturing. This wasn't just an engineering debate. It was an economic and philosophical one. On one hand, you have the meticulous, craft-driven approach of the old world. On the other, the pragmatic, production-focused mindset of the new world. And for nearly a century, these two systems would compete, coexist, and cause endless headaches for anyone trying to repair a British car with American tools, or vice versa. The incompatibility was a massive problem. Imagine being a mechanic and having two sets of wrenches, two sets of taps and dies, and two sets of fasteners that looked almost identical, but were fundamentally incompatible. It was a logistical nightmare. This rivalry reached a critical point during the World Wars, when the US and UK had to collaborate on building tanks, planes, and ships. The thread difference became a major bottleneck. Parts made in America wouldn't fit with parts made in Britain. A simple repair could be delayed for days waiting for the right kind of bolt. It was a lesson learned the hard way. In a globalized world, incompatible standards are a liability. This wartime frustration was the catalyst that would eventually force these two industrial giants to sit down and hash out a compromise. But that compromise, the unified thread standard, is a story for our next video. We'll explore how they finally blended the best of both worlds, creating the system that dominates much of the globe today. We'll look at why the 60-degree angle ultimately won out, but with a nod to Whitworth's rounded root design. It's a tale of compromise, collaboration, and the birth of the modern screw thread. So the next time you see a bolt, think about that angle. Is it a 55-degree echo of the British Empire, or a 60-degree testament to American industrial might? It's amazing how a tiny 5-degree difference can tell such a big story about history, technology, and the different ways we approach solving a problem. This whole saga really shows that in engineering, there's rarely a single right answer. There are just different solutions with different trade-offs. Alright, so we've seen how messy things were before Whitworth came along. But how does a good idea actually take over the world? Well, it often needs a little push from a big industry. And in the 19th century, there was no industry bigger, faster, or more revolutionary than the railways. Imagine Britain in the 1830s and 40s. A railway mania is sweeping the nation. Tracks are being laid at a furious pace, connecting cities, towns, and ports like never before. It was the internet of its day, a massive, sprawling network that was changing everything. But this network had a huge, hidden problem. Each railway company was its own little kingdom. You had the Great Western Railway, the London and North Western, the Midland Railway, dozens and dozens of them. And each one built its own locomotives, its own carriages, its own everything. And you guessed it, they all used their own unique, non-standardized nuts and bolts. So picture this, a train from the London and North Western Railway breaks down. A simple bolt is sheared off on a connecting rod. The train limps into a station that happens to be owned by the Midland Railway. The station's workshop is full of spare parts, bins overflowing with nuts and bolts. But not a single one fits the stranded locomotive. Why? Because the threads are all different. The pitch is wrong, the angle is wrong. The diameter is a fraction of an inch off. This wasn't a rare occurrence. It was a daily nightmare. A train, this marvel of modern engineering, worth thousands of pounds and carrying vital goods or impatient passengers could be rendered completely useless by a single 10-penny bolt. The solution, it was absurdly inefficient. The broken train would have to wait, sometimes for days, for a specific, custom-made part to be shipped from its home workshop, maybe hundreds of miles away. Or the local mechanics would have to fire up their forge and try to handcraft a replacement bolt on the spot, a time-consuming and often imprecise process. The cost of this was staggering. It wasn't just the price of the repair. It was the cost of the delay. An entire railway line could be blocked. Goods would spoil. Business deals would be missed. Passengers would be furious. All that incredible speed and efficiency promised by the railway could grind to a halt because of incompatible screws. Railway engineers and managers were tearing their hair out. They were practical people, obsessed with efficiency and timetables. This chaos was an affront to their very nature. They needed a system. They needed a standard. And that's where Joseph Whitworth's quiet revolution meets the roaring power of the steam engine. It wasn't a dramatic, headline-grabbing event. It was more of a slow, logical, administrative creep. Railway companies started talking to each other. Engineers from competing lines met and shared their frustrations. And one name kept coming up, Whitworth. His system of standardized threads wasn't just a theory anymore. It was a proven, practical solution being used in the best workshops. The change started small. A few forward-thinking railway lines began specifying Whitworth threads for all new locomotives and rolling stock they ordered. They told their suppliers, the big engineering firms like Robert Stevenson and Company, that all bolts, nuts, and screws had to conform to the Whitworth standard. The benefits were immediate and obvious. Now, a locomotive could be repaired at any major station along its route, regardless of which company owned the station. A mechanic in Bristol could fix a train from Manchester using a standard bolt straight from his parts bin. The massive, complex logistical headache of stocking thousands of unique, company-specific spare parts began to disappear. Instead of needing a dedicated storeroom for every single type of locomotive they serviced, workshops could now have a single, universal set of fasteners. This was a logistical victory of immense proportions. It dramatically reduced inventory costs, simplified maintenance, and, most importantly, slashed downtime. Trains were kept running, schedules were met. The entire network became more reliable, more efficient, and more profitable. This process created a powerful feedback loop. As more railways adopted the Whitworth standard, it became the default. Manufacturers found it easier and cheaper to produce one standard type of bolt rather than dozens of custom varieties. It was a classic case of network effects. The more people who used the standard, the more valuable the standard became for everyone. By the 1860s, the battle was essentially over. The Whitworth thread had conquered the railways. It wasn't through a government decree or a dramatic invention. It was a quiet administrative decision, repeated across dozens of company boardrooms, driven by the simple, undeniable logic of efficiency and cost saving. The railway, the great connector of the physical world, had become the vehicle that carried standardization into every corner of British industry. This quiet victory on the railways laid the groundwork for everything that came next. The standard that fixed the trains would go on to build ships, bridges, factories, and eventually the entire modern industrial world. It's a powerful reminder that sometimes the most profound revolutions aren't the loud ones, but the ones that happen quietly in the background, one standardized bolt at a time. Alright, let's pick up where we left off. So, we've seen how Britain and America, with their Whitworth and Sellers threads, were kind of going their own ways. But what about the rest of Europe? Well, a lot of them were looking at the metric system and thinking, this is the future. It's clean, it's logical, it's based on tens. Why can't we have a thread system that's just as sensible? This idea had been bubbling for a while. Various European countries had come up with their own metric thread standards, which you can imagine was just creating a whole new set of compatibility problems. It was like everyone speaking a different dialect of the same language. You could sort of understand each other, but it was messy. The need for a single, unified, international metric thread system was becoming painfully obvious. So, in 1898, a bunch of the brightest engineering minds from across Europe decided to do something about it. They all packed their bags and headed to Zurich, Switzerland. This wasn't just any old meeting. This was the International Congress for the Unification of Screw Threads. Sounds grand, doesn't it? And it was. This was a pivotal moment, a chance to finally create a universal language for making things. Picture the scene, a conference hall in Zurich, filled with serious-looking men in starched collars and impressive mustaches. Engineers from France, Germany, Switzerland, and other nations, all gathered with a common goal. The air is probably thick with cigar smoke and the weight of expectation. They're not there to debate politics or art. They're there to argue about millimeters and pitch angles. It might sound dry, but for the industrial world, this was high drama. The French delegation, predictably, was a huge proponent of the metric system. They'd been using it for over a century and had already developed their own metric thread, the Système Francaise. They came to Zurich hoping to convince everyone that their system was the best one to adopt. It was logical, based on a simple formula, and already in use. But the Germans had other ideas. German engineering was on a meteoric rise, and they had been developing their own, slightly different metric thread standards. They weren't just going to roll over and accept the French system without a fight. They had their own data, their own theories on what made the most robust and efficient thread. So right away, you have this classic Franco-German rivalry playing out, not on a battlefield, but over the microscopic grooves on a piece of metal. The Swiss, being the hosts and famously neutral, tried to act as mediators. They had their own thread standards too, of course, but their main interest was in finding a compromise that everyone could agree on. They knew that a fractured Europe, unable to even agree on how to make a bolt, was bad for business and bad for progress. So the debates began, and they were intense. These engineers would spend hours, days, hunched over technical drawings and charts. They argued about the flank angle of the thread. Should it be 60 degrees, like the American seller's thread, or something else? A 60-degree angle was easy to machine, which was a big plus. But was it the strongest? Then there was the debate over the profile. Should the crest and root of the thread be flat, like the seller's thread, or rounded, like the Whitworth? Flat crests were simpler to cut, but rounded ones were stronger and more resistant to stripping and fatigue. This was a huge point of contention. The French system had flat tops, but many engineers, remembering Whitworth's arguments, favored the durability of a rounded profile. And of course, the biggest debate of all, the specific combinations of diameter and pitch. This is the heart of any thread standard. For a given diameter, say 10 millimeters, what should the pitch be? 1 millimeter? 1.5? Every decision was a trade-off. A coarser pitch with fewer threads per inch meant faster assembly but potentially less clamping force and a weaker connection. A finer pitch was stronger but took longer to screw in and was more susceptible to damage and cross-threading. They had to create a whole series of standard sizes, from tiny screws for watches and scientific instruments, all the way up to massive bolts for steam engines and bridges. Each size needed its own perfectly chosen pitch. The delegates would propose a set of numbers, and then the arguments would start. That pitch is too fine for a 12-millimeter bolt. It will strip under load. One engineer might exclaim, "But your proposal is too coarse. It won't provide enough clamping force for high-pressure applications." Another would retort, these weren't just opinions. They were backed by calculations, experiments, and years of practical experience. They were trying to create a system that was not just theoretically sound, but also practical for the machinists on the factory floor. It had to be easy to manufacture, easy to inspect, and reliable in the field. While these engineers were locked in their stuffy conference room, the world outside wasn't waiting. The second industrial revolution was in full swing. Factories were churning out new machines, automobiles were just starting to appear on the roads, and the first airplanes were only a few years away from taking flight. All of this new technology depended on fasteners, on millions and millions of nuts and bolts. The pressure to come to an agreement was immense. After days of intense negotiation, haggling, and redrawing proposals, they started to find common ground. It was a process of give and take. Maybe the French would concede on a particular pitch size if the Germans agreed to a specific thread angle. Slowly, painstakingly, a new system began to take shape. They agreed on a 60-degree flank angle, a compromise that took the best from the American system's ease of manufacturing. And for the profile, they made a crucial decision. Instead of a fully rounded root and crest like Whitworth, or a fully flat one like Sellers, they created a hybrid. The new international metric thread would have a flat crest, but a rounded root. This was a brilliant compromise. The flat crest was easier to make, while the rounded root provided that all-important strength and resistance to fatigue, cracking where the stress is highest. Finally, they hammered out a comprehensive table of diameters and pitches. This became known as the Systeme International, or SI thread. It was a beautiful, logical system. For the most part, the pitch was directly related to the diameter in a simple way. It was everything the metric system was supposed to be: rational, standardized, and universal. The delegates at the 1898 Zurich Congress left feeling triumphant. They had created something that they believed would change the world. They had laid the foundation for a truly global manufacturing standard. They published their findings, and the new SI metric thread standard was born. But as we've learned, creating a standard is one thing. Getting everyone to actually use it is a completely different battle. The proposal from Zurich was elegant and well thought out, but it wasn't an international law. Countries, and more importantly, individual companies, had to choose to adopt it. And that process, as you might guess, was going to be anything but simple. The British and the Americans, with their massive industrial might and their own established inch-based systems, were watching from the sidelines. They weren't at the Zurich Congress, and they weren't about to abandon their systems overnight. The thread wars were far from over. In fact, they were about to get even more complicated. We'll dive into that messy adoption process and the resistance the new metric standard faced in our next part. The story of screw threads is a surprisingly dramatic one. We talked about how brilliant engineers like Whitworth and Sellers tried to bring order to the chaos of fasteners. They created standards, hoping to make life easier for everyone. But as the world barreled into the 20th century, bringing with it 2 devastating world wars, it became painfully clear that their dream of universal compatibility was far from reality. And on the battlefield, this wasn't just an inconvenience, it was a matter of life and death. Imagine this. It's World War II. A British tank, a crucial piece of machinery on the front lines, has broken down. An American engineering corps, brave and skilled, rushes to get it running again. They open up the engine compartment, tools in hand, ready to replace a damaged part. They find the right size bolt, or so they think. They try to screw it in. It goes in a little, then stops. It won't tighten. They try another. Same problem. The American-made bolts simply will not fit the British-made engine. Why? Because the threads are different. The American bolt has a 60-degree thread angle, and the British one has a 55-degree angle. They are fundamentally incompatible. This wasn't a rare occurrence. This was a daily, infuriating, and dangerous reality for the Allied forces. While soldiers were fighting on the front, engineers were fighting their own battle against incompatible parts. Every piece of equipment, from planes and tanks to jeeps and rifles, was a complex puzzle of nuts and bolts. The United States, the arsenal of democracy, was churning out incredible amounts of machinery and spare parts to support the war effort. But when those American-made parts arrived in Europe or the Pacific, they often couldn't be used to repair British or Canadian equipment. The logistical nightmare was staggering. You couldn't just send a box of half-inch bolts to the front. You had to send a box of American half-inch bolts and a separate box of British half-inch bolts. This meant double the inventory, double the shipping weight, and double the confusion. Warehouses became a chaotic mess of bins filled with nearly identical-looking, yet completely incompatible fasteners. A mechanic in the field, working under immense pressure, often in the dark and under fire, would have to waste precious time hunting for the exact right part from the correct country of origin. A simple repair that should have taken minutes could stretch into hours. And in a war, hours could mean the difference between a tank rejoining the fight or being abandoned to the enemy. The frustration was immense. There are countless stories of mechanics having to retap threads in the field, a difficult and time-consuming process, or even cannibalizing parts from one broken-down machine to fix another. This wasn't efficient. It wasn't sustainable. It was a crisis born from a simple, overlooked detail, the shape of the groove on a piece of metal. Even before the Second World War, during World War I, this issue had already reared its ugly head. The lack of a common standard between the U.S. and its allies had caused significant delays and inefficiencies. Committees were formed, discussions were had, but little progress was made. The problem was just seen as a technical annoyance, not the critical strategic weakness it truly was. But by World War II, the scale of the problem was too big to ignore. The sheer volume of international cooperation required to fight a global war made the screw thread issue a top-level concern. High-ranking officials in Washington and London realized that their armies were being hamstrung by something as mundane as a bolt. It was William Albad, an American industrialist and key figure in the War Production Board, who really championed the cause. Having witnessed the chaos firsthand, he relentlessly pushed for a solution. He argued that a common standard was not just a matter of convenience. It was a matter of national security and military effectiveness. He organized conferences and brought together engineers, manufacturers, and military leaders from the United States, Great Britain, and Canada. The initial meetings were tense. Decades of industrial habit and national pride were at stake. The British were proud of their Whitworth standard, with its 55-degree angle, which they believed held better under vibration. The Americans were equally committed to their Sellers standard, with its 60-degree angle, which was easier and cheaper to manufacture. For either side to give way felt like admitting their own system was inferior. But the war provided a powerful, undeniable argument. Story after story from the front lines highlighted the absurdity of the situation. Imagine a brand new Rolls-Royce Merlin engine, the powerhouse of the Spitfire and Mustang fighters, being shipped from Britain to an American maintenance depot. The American mechanics, some of the best in the world, would be practically helpless if they didn't have the specific British threaded tools and fasteners. The engine might as well have been a sealed box. Slowly, painstakingly, a compromise began to take shape. The engineers went back to basics. They analyzed the strengths and weaknesses of both systems. The goal was to create a new standard that would be a true hybrid, taking the best features of both the Whitworth and the Sellers threads. It had to be strong, reliable, and easy to manufacture. After years of negotiation, calculation, and testing, a breakthrough was finally achieved. In 1949, shortly after the war ended, representatives from the United States, the United Kingdom, and Canada met in Washington, D.C. and signed an accord. This agreement established the Unified Thread Standard, or UTS. The new UTS was a brilliant compromise. It adopted the 60-degree thread angle from the American Sellers profile, which made it easier to mass produce. but it also incorporated a rounded root, similar to the British Whitworth design, which improved its fatigue resistance and made it stronger. It was the best of both worlds, a standard forged in the fires of conflict and cooperation. The adoption of the Unified Thread Standard was a landmark moment in the history of engineering. It was a recognition that, in an increasingly interconnected world, collaboration and standardization are not just good ideas, they are essential. The logistical chaos of World War II served as a harsh but necessary lesson. Today, if you walk into a hardware store in North America and pick up a bolt, chances are it uses the Unified National Course, UNC, or Unified National Fine, UNF thread, both of which are part of the UTS. This standard has become the backbone of manufacturing and construction across a huge portion of the globe. But the story doesn't end there. As the world was unifying its imperial threads, another system was quietly gaining ground. A system based on an entirely different way of thinking about measurement, the metric system. In our next video, we'll dive into the rise of the metric thread standard and the ongoing thread war that continues to this day. It's a battle of millimeters versus inches, and it affects everything you use, every single day. We talked about how Whitworth's imperial thread system and the metric system caused a huge mess during World War II, leading to tragic equipment failures and loss of life. After the war, everyone realized this couldn't go on. The world needed a single, unified standard. So, in the quiet aftermath of the war, a new organization was born. On February 23, 1947, in London, the International Organization for Standardization, or ISO, was officially founded. This wasn't some flashy, high-profile event. It was a gathering of engineers and scientists who understood that for the world to rebuild and connect, they needed to agree on the small things first. And their very first task, the topic of their first ever meeting, wasn't what you might expect. It wasn't about threads or bolts or even wrenches. The very first standard they needed to agree on, which would become ISO standard number 1, was something far more fundamental. What was it? Temperature. Specifically, the standard reference temperature for industrial length measurements. You see, metal expands when it's hot and contracts when it's cold. If you're measuring a part in a warm factory in one country, and your counterpart is measuring the same part in a colder factory somewhere else, your measurements won't match, even if you're using the exact same tools. This tiny difference could be enough to make a critical component fail. So before they could even begin to talk about unifying screw threads, they had to agree on the temperature at which all measurements would be based. After much deliberation, they settled on 20 degrees Celsius, which is 68 degrees Fahrenheit. This became the bedrock upon which all other international mechanical standards would be built. It was a seemingly small decision, but it was the crucial first step. It established a common ground, a shared reality for engineers all over the world. With this fundamental agreement in place, the stage was finally set to tackle the real beast, creating a single global standard for screw threads. This monumental task would lead to the birth of the isometric screw thread, the system that dominates our world today. But the path to that standard was anything but smooth. It was a story of fierce debate, national pride, and brilliant engineering compromises. And that's exactly what we'll dive into next time. Alright, let's dive back into the world of threads. We saw how Whitworth and Sellers battled it out, creating a sort of thread civil war between Britain and America. But while they were arguing, another contender was quietly rising, one that would eventually conquer the world. I'm talking, of course, about the metric thread. Now, the idea of a metric-based screw thread wasn't new. It had been floating around Europe since the late 18th century, but it never really caught on. Why? Well, for one, the metric system itself was still finding its feet. Plus, every country, every workshop, even every individual mechanic seemed to have their own standard. It was chaos. Imagine trying to repair a French machine with German bolts. Good luck with that. The first real, coordinated effort to standardize metric threads came from Switzerland in the late 1800s with the Thury thread, mainly for watches and scientific instruments. It was precise, but it was also complex and didn't scale up well for heavy industry. Then came the French with their Système International, or SI thread. This one was a big deal. It had a 60-degree profile, just like the Sellers thread, and it was designed to be a comprehensive system for all sorts of applications. It gained a lot of traction across continental Europe, but here's the thing about standards. They only work if everyone agrees to use them. While Europe was slowly gravitating towards the French SI thread, America was all in on Sellers, and the British Empire was firmly committed to Whitworth. The world was divided into 3 major thread blocks. This wasn't just an inconvenience. It was a massive headache for international trade, manufacturing, and especially for military alliances. Think about World War I and World War II allies trying to share equipment, repair vehicles, and supply parts, but nothing fits together. A British nut won't go on an American bolt. It was a logistical nightmare. After the Second World War, the world was desperate for a fresh start. There was a huge push for international cooperation, and that included engineering standards. In 1947, the International Organization for Standardization, or ISO, was founded. One of its very first and most important tasks was to create a single unified screw thread standard for the entire planet. This was not going to be easy. You had the inch-based camp, led by the US, UK, and Canada, and the metric camp, represented by most of continental Europe. The inch camp argued that their systems were already mature, widely used, and proven in the crucible of war. The metric camp countered that their system was simpler, more logical, and based on the decimal system, making calculations a breeze. The negotiations were intense. For a while, it looked like they might just create yet another competing standard. But a compromise was reached. The inch-based countries agreed to unify their own threads first, creating the Unified Thread Standard, or UTS, which we still use today, the UNC and UNF threads you see everywhere in the US. This was a big step, but it was meant to be temporary, a bridge to an eventual global standard. Meanwhile, the ISO got to work on the ultimate goal, the isometric thread. They took the best bits from the existing metric systems, primarily the French SI and the German metric threads, and refined them. They kept the 60-degree flank angle, which had proven its strength and ease of manufacture. They created a logical, systematic series of diameters and pitches, designated by the letter M. M8, for example, means a metric thread with an 8mm nominal diameter. Simple, elegant, and unambiguous. The design of the M-series thread was a masterpiece of engineering compromise. Unlike the Whitworth thread with its rounded crests and roots, and unlike the Sellers thread with its flat ones, the isometric thread has flat crests and rounded roots. The flat crests make it easier to manufacture and measure, while the rounded roots, thanks to a larger root radius, significantly improve fatigue strength by reducing stress concentrations. It was the best of both worlds. The ISO published the basic standards for the M-series metric thread in the 1950s and 60s, and then the slow, grinding, decade-long transition began. This wasn't a switch that could be flipped overnight. It was a monumental undertaking. Think about it. Every factory in the world had to decide when or if to make the change. For companies and countries already using metric, the switch was relatively easy. It was more of an update than a revolution. But for countries in the inch-based world like the UK and eventually the US, it was a different story. It meant redrawing tens of thousands of blueprints. It meant retooling multi-million-dollar machines. It meant retraining an entire generation of engineers, machinists, and mechanics who had spent their entire lives thinking in inches, fractions and threads per inch. Manuals had to be reprinted. Supply chains had to be completely overhauled. You couldn't just stop making imperial fasteners. For decades, you'd need to supply both for repairs and maintenance on older equipment. Garages and workshops suddenly needed 2 sets of everything: wrenches, taps, dies, and a dizzying array of nuts and bolts. The transition happened in waves. Japan, a rising industrial power, adopted the isometric standard enthusiastically in the mid-1960s, a move that supercharged its export-driven economy. Cars and electronics made in Japan could be sold and serviced anywhere in the metric world with ease. This put immense pressure on other countries. The United Kingdom, the birthplace of the Whitworth thread, began its official metrication program in 1965. It was a slow and sometimes painful process, met with a lot of resistance, but industry by industry, the changeover happened. Old British cars are famous for having a wild mix of Whitworth, BA, and later metric and unified fasteners, a testament to this transitional period. The last major holdout was, and in many ways still is, the United States. The Metric Conversion Act of 1975 declared metric as the preferred system of measurement for U.S. trade and commerce, but it made conversion voluntary. The U.S. auto industry began its slow shift in the late 70s and 80s, largely to be more competitive in a global market. But consumer resistance and the sheer cost of converting a continental-sized economy meant that the U.S. remains a place where both systems coexist, often to the frustration of everyone. If you've ever worked on a car from the 90s, you know the pain of needing both a 30mm and a half-inch wrench for the same job. Today, the isometric thread is, without a doubt, the dominant global standard. It's the default for almost all new product design around the world. Its rise wasn't due to a single invention or a brilliant marketing campaign. It was a slow, deliberate, and sometimes difficult victory of logic and cooperation over tradition and regionalism. It was the result of decades of work by thousands of engineers who understood that, for the world to connect, our machines had to connect first. And that connection starts with something as small and as important as the thread of a screw. But the story doesn't end there. Even within the world of metric threads, there are variations, fine threads, coarse threads, and special profiles for specific jobs. In our next episode, we'll dive deeper into the M series, exploring why you might choose a fine thread over a coarse one, and we'll look at some of the specialized threads that hold our modern world together, from the pipes under our streets to the rockets that fly to space. If you've ever walked through a hardware store, you've seen a fraction of what I'm about to describe. But imagine that scaled up 1,000,000 times. We've talked about the history, the physics, the incredible journey of the humble screw thread. But where does that journey lead in our modern world? It leads to a place that, on the surface, might seem incredibly boring, but is actually one of the most vital and fascinating hubs of modern civilization, the automated fastener warehouse. Picture this: vast, cavernous buildings stretching as far as the eye can see. There are no bustling crowds, no clanging of hammers. Instead, there's a quiet, rhythmic hum. Aisles tower stories high, lined with thousands upon thousands of identical plastic bins. And in these bins, resting silently, are not just thousands, but millions, even billions of fasteners. This isn't a chaotic jumble, it's a cathedral of order. In one bin, you'll find 1,000,000 M8 hex bolts, each one a perfect, indistinguishable clone of the next. A few aisles over, a mountain of 1/4 to 20 nuts, their internal threads cut to a precision measured in micrometers. Another section holds countless self-tapping screws, their sharp points gleaming under the fluorescent lights. The air is cool and still, punctuated only by the whir of robotic arms and the silent glide of autonomous guided vehicles, or GVs. These aren't the warehouses of the past. Here, a complex software brain, a warehouse management system, orchestrates everything. An order comes in from a car factory in Detroit for 10,000 specific bolts. The system instantly knows their exact location, aisle 73, shelf D, bin 12. It dispatches a robot, which glides silently down the aisle, its arm extending to retrieve the precise bin. It brings it to a picking station, where a human worker or another robot counts out the exact number needed, packs them, and sends them on their way. The entire process is a ballet of efficiency, designed to minimize error and maximize speed. Every single item in this building has a barcode, a digital fingerprint that tells its entire life story, where it was forged, what batch of steel it came from, its exact dimensions, and its tensile strength. This level of traceability is non-negotiable in industries like aerospace or medical equipment, where a single faulty bolt isn't just an inconvenience. It could be a catastrophe. This warehouse isn't just storing metal parts. It's storing trust. It's storing the guarantee that the components holding our world together are flawless. Let's zoom in on one of those bins. Inside we see M10 bolts. They look simple, almost trivial, but their existence is a modern miracle. Some of these bolts might have been forged in a factory in Japan. The nuts they will eventually meet could be manufactured in Germany, and the wrench that tightens them might be made in the United States. They will all come together, perhaps on an assembly line in Mexico, to build a wind turbine destined for the North Sea, and they will fit perfectly. This seamless interoperability is the quiet triumph of standardization. It's the result of decades of agreements, of engineers from competing nations and companies sitting down and deciding that an M10 thread should have a pitch of 1.5 millimeters, no matter where in the world it's made. This boring perfection is the invisible engine of globalization. It means a mechanic in rural Australia can repair a tractor from Italy with a part ordered from a supplier in Korea, confident that it will work. It's the reason you can buy a flat-pack piece of furniture and have all the little screws and bits fit together as intended. Think about the sheer scale. A single modern car contains over 3,000 threaded fasteners. A commercial airliner like a Boeing 747, it has millions. Now multiply that by all the cars, planes, bridges, buildings, smartphones, and coffee machines produced every single day. The demand is astronomical, and it's all supplied by these silent, orderly warehouses. They are the buffer, the great reservoir that keeps the machinery of the world humming. When a factory needs parts, they don't have to wait for them to be manufactured. They are already here, waiting. This just-in-time delivery system, made possible by these logistics hubs, is the backbone of modern manufacturing. It's easy to be impressed by the final product, the gleaming skyscraper, the powerful engine, the sleek laptop. We celebrate the vision of the architect and the genius of the engineer, but we often forget the silent, unglamorous components that make it all possible. We forget the logistics network that ensures every single one of those millions of parts arrives at the right place, at the right time. The perfection of the screw thread, which we've discussed, is only half the story. The other half is the perfection of the system that delivers it. This warehouse represents the peak of a long historical arc. We've moved from the blacksmith hand-forging a single, unique bolt for a specific hole to this, a global, interconnected system of mass-produced, interchangeable parts. It's a world where precision is not a luxury, but a given. The quiet hum of this warehouse is the sound of reliability. It's the sound of a world that works. It's the physical manifestation of a promise that the parts will fit, the machines will run, and our complex society will hold together. And while it may seem like the end of the story, this level of standardization and automation actually opens the door to new innovations and challenges. What happens when we need new types of fasteners for new materials, like carbon fiber composites? How does 3D printing or additive manufacturing change the game when we can print a custom bolt on site? The world of fasteners is far from static. The silent bins in this warehouse tell a story of incredible success, but they also set the stage for the next chapter. And that's exactly what we'll be exploring in our next video. We'll look at the future of fasteners, from smart bolts with embedded sensors to the exotic materials pushing the boundaries of engineering. Thanks for joining me on this tour of the unsung hero of the modern world. It's a testament to how the most profound innovations are often the ones that become so reliable, so ubiquitous, that we forget they're even there. If you found this fascinating, make sure you're subscribed so you don't miss what's coming next. See you then.